Welcome to the second session of our FDP on AI in medical imaging and diagnostics. Yeah, am I audible? Am I audible? Yeah. So let me share my screen first. Yeah. So is my screen visible? I will make it full screen. Just please confirm that whether it is visible or not. Okay. Okay, thank you. So I'll check regularly the chat box, right? So I mean, anytime you can stop me. I mean, I'll just check the chat box, right? If you are having any queries, probably this is the easiest session, right? You'll be having. So because you all are very much aware about transfer learning and all, but there are few things which are very, very important for us to know, right? While applying the transfer learning, we should keep in our mind that whether we should have, because it basically there are several factors that can influence, right, the results if you are applying transfer learning. Right. So before I discuss what do you mean by transfer learning and some of its applications, right? So today I'm also going to show you some of the case studies, I mean, which we did a few years back using transfer learning, and also by designing our own approach, you can say by designing some of the lightweight models. Many of the speakers have talked about the importance of the compressed models, right, in medical imaging domain, because most of the time we don't have much amount of data. So can we have lightweight models of, you can say, same capability, right? Same capability with the heavy models. We'll talk about it later on how to, I mean, when the models are said to be lightweight models, and I mean, whether it should be even more lighter or not, and if it is even more lighter, then what will happen, like that. So there are multiple things which I will cover in this particular lecture. So if you look at the content of this lecture, so I'll start with the evolution of the convolutional neural network architecture and how it got evolved, right? So over the years, since mostly since 2012, when AlexNet came into the picture, although the concept was not new, I will also share some of the important information and interesting information about convolutional neural network and its history as well. And the most important thing is what are the limitations of working with CNNs, right? I mean, whenever we are applying CNNs, yes, we know that it is giving better result than the traditional neural network. And I think in my last lecture, we have talked about why convolutional neural network is performing better over the images or videos compared to the traditional neural network. And we have also talked about the limitations, right, of limitations of using traditional neural network. And mostly we discussed about two things, like the computational complexity is going to be very, very high, because what we are doing is we are simply unrolling a two-dimensional or three-dimensional matrix into a one-dimensional vector, right? And where every hidden neuron is connected to every other neurons in the preceding layer. So that is why the number of parameters is going to be very, very high. At the same time, by converting the image matrix into a vector, we are losing spatial information, which is very, very important. So these are the two limitations, major limitations we have seen in case of traditional neural network, and we'll see how this convolutional neural network can help us in avoiding those type of challenges, right? And basically how to deal with those type of challenges. And today's main focus is transfer learning, right? Because it is very, very useful in the domain of medical imaging, not only in the domain of medical imaging, but also in the domain of computer vision. You will see its, uses, when to use, what are the different strategies we have in transfer learning, and whether those strategies are dependent on some factors or not. If it is dependent on some factors, then what are those factors? We'll also look at into it. And at the same time, we will also talk about what are the other ways to use convolutional neural network. And one of the, of course, ways is transfer learning. We'll also see. And we will also see what is the basic difference between classification and segmentation, and some of the architectures, convolutional neural network based architectures, which are commonly useful or used for segmenting medical images or segmenting images, right? And there are a few architectures which are mainly designed or dedicatedly designed for solving medical imaging tasks and later been adapted to solve image segmentation or natural image segmentation tasks like that. And there are a few case studies like this. Just I will show you some of the results and what was in our mind that time. Why did we design such type of architectures and all? And finally, the challenges, right? Most of the speakers have already talked about several types of challenges, right? So I will just summarize the challenges, whatever the challenges we have seen till now, right? So, while applying the convolutional neural network architecture. Fine. So I will just spend 1 minute of time to discuss about convolutional neural network. I'm assuming that all of you are very much aware about convolutional neural network, and this is how actually one of the simplest convolutional neural network looks like. You can see, right, where input is an image, let's say, or set of images here, and then there are certain layers like the hidden layers you have seen in case of traditional neural network, and at the end you will find some of the dense layers, right? So this is a sequential convolutional neural network architecture, which was adopted, right? Maybe 5 to 10 years before, right? Now, if you look at the architecture of convolutional neural network, it is pretty different to the sequential architectures, right? Somewhat even more deeper, you will find the recent architecture. Sometimes it is even wider, right? So if you just look at, here the hidden layers are something very different from the hidden layers which we have seen in case of traditional neural network, where only in the hidden layers we were having the neurons. But here, the neurons were connected through weights and biases. And here the weights and biases are in the convolutional layer, it is something very different, right? So if you look at any convolutional neural network architectures, you will find three basic layers, or you can say conventional layers that are convolutional layer, ReLU layer, and pooling layers, right? So this convolutional layer is going to be very, very important for us, and because this is where actually we are trying to extract some of the meaningful informations from the images. And what we usually do here, we usually put a lot of filters over the input images, right? And those filters can be of size anything, can be of size 3x3, 5x5, 7x7, even more than that. Sometimes we also use 1x1 convolutions in some of the networks, but for some other purpose, which are known as bottleneck layers, right? So mostly 3x3 you will find 3x3, 5x5, 7x7. In some of the architectures, you will also find there are some filters having size even 11x11. If you just look at the AlexNet architecture side, so we'll talk about it. Is there any need of directly using such type of large filters? Large size filters or not? So if you remember, we discussed in case of traditional neural network that every neuron is connected to every other neurons. If you look at just last three layers over here, these are like dense layers or fully connected layers, very similar to the neurons, or we can say the layers, right? In case of traditional neural network. So here every neuron, right? If you look at the last three layers, where every neuron is connected to every neurons in the previous layer, right? And that is why in case of traditional neural network, I said that is the number of parameters is going to be very, very high. But we are not doing the same thing in the convolutional layer. So in the convolutional layer, what we are usually do? So what we usually do is we apply the convolution over a particular region, which is known as a receptive field of that particular image, right? So if you are applying a 3x3 filter, so you will choose a 3x3 window in the input image, and then you will just slide that filter, right? And it all depends upon the different factors like what is the stride value, what is the padding value, right? So whether you can apply the filters on the boundary or you can say the boundary pixels or not. So to apply that, we need padding values and all, right? You have to pad zeros, or there are been multiple ways to pad. So zero padding is the most, you can say the common one, right? So we are applying what we are doing, and we are again applying the same filter over all the images, right? So those were from signal processing background. They better know what do you mean by convolution and why convolution, why we are applying convolution, why not other operations. It has a lot of significance, right? And there is a lot of importance in signal processing also. And it satisfies a lot of properties like one of the property is translation invariance. at the same or shift in variance, which is very, very important, right? In case of image classification or other types of applications. At the same time, there is another property which is very, very important, which convolution satisfies easily, is basically localization property, which is very, very important. So localization, shift invariance properties are very, very useful properties of convolution, and that is where we are very much interested in that. And if you just go back to the history, you will also find some of the biological inspirations, right, of the convolution operations, right? So basically, why we apply convolution? Basically, we want to extract different types of informations from the images. We are not only applying a single filter, we are applying a set of filters to extract different types of informations, and then we are repeating, right, over different layers. That means the same kind of operations are repeated over the layers to basically extract the hierarchical features, right? And also we have seen in some of the lectures that how this convolution is helping us in extracting the features at different levels, right? I mean, there are low-level features, there are mid-level features, there are high-level features, which I'll be also showing later on. And at the end, and then which is basically followed by, of course, I mean, a ReLU layer, which is an active nonlinear activation function layer. So it is very similar to the traditional convolutional neural network, where after summation or after applying uh, the summation operation and all, so we used to apply some sort of activation function, and we all know it is just to establish the nonlinearity in the network, right? And not only the ReLU, but also the variant of the ReLU, because ReLU has also some limitations as well, right? So followed by some of the pooling layers, which is a kind of downsampling layer. We are very much acquainted with that. What are downsampling layers? And it basically helps in reducing, right, the feature map. The feature maps are nothing but the output after applying a convolution layer, right? After applying convolution operation, whatever you are getting is nothing but a feature map, right? And these box kind of structures, whatever you are looking at here, so it's nothing but, so if you are applying one particular filter over this, right, the filter should have similar depth with the input image. And then after applying the filter, right, it is simply a dot product. This convolution over here is, right. So we will get a single feature map. And if you are applying, let's say 10 number of filters, so you will get 10 number of basically feature maps, right? And if you just stack them together, you will just get a volume like this, known as feature volume or feature map volume, like that, right? So that means we are applying multiple filters, and the goal is to extract different types of informations from each of the filters, right? And now you see also the size is getting reduced over the layers. This is only because of the pooling layers which we have. It's a kind of downsampling layer. It also helps in reducing, right, the of parameters. Or else if you're not downsampling the feature map, so the number of parameters is going to be very, very high, and again it will be, right, difficult for us to avoid the problems like overfitting and all, right? So at the end, in the earlier convolutional neural networks, so you'll find at the end, researchers have always put more than two or more than three number of dense layers, right? And these because of these dense layers, so people have found that these dense layers are nothing but causing or basically leading to high number of parameters. So that's why the current trend is not to use much number of dense layers. I mean, just to use the last layer, which is just a classification layer containing number of neurons equal to the number of classes, right? Because it accommodates a lot of parameters, right? I mean, learnable parameters. So if you just look at this architecture, although looks very different from the traditional neural network, but it is also carrying the same principle, having the weights and biases at every layer. Not only, I mean, not every layer, not like in the ReLU layer or in the pooling layers, only in some of the layers like convolutional layers, and here like the dense layers, right? Because not every layer contains here parameters. Fine. And as I mentioned already, that CNN learns to detect different features of an image using different number of hidden layers. So every hidden layer increases the complexity of the learned imaging feature. Like the first hidden layer would help us in learning the edges, the color blobs. So maybe the intermediate layers will help us learning the combinations of the edges or shape-based features like that. And the final layers will help us in estimating the shapes or all, right? The complex shapes and all. I mean, basically the abstraction and the hierarchical features as well. So we look at the history of convolutional neural networks. So these are not new. So it was introduced in late 80s by Professor Licon. And then the question obviously that comes to your mind, then why we are discussing convolutional neural network right now, right? And why it has taken 3 decades of time to impact the vision community. So we can say right algorithm at a wrong time, right? There was no storage capability of the computers to store the millions of the images, and there was no even a GPU at that time. So we have all those things right now. So that's why we're very much interested in designing some sort of convolutional neural network algorithms. So this is the first architecture, which is known as LeNet architecture, was designed to solve a digit classification problem, which is a 10 class classification problem. If you just look at the last layer, it contains 10 neurons. Of course, it is solving 10 class classification problem, and there are some convolutional layers followed by subsampling or downsampling. We can call it as even pooling layer, right? And you can see some of the fully connected layers at the end containing 120 and 84 neurons like that. So then there was a huge gap around 1998 to 2012, and this is the major breakthrough architecture, right? Professor Hinton and his group proposed in 2012, and this particular architecture was also winner of a challenge, IELS VRC challenge. It's a very popular challenge, and because of that challenge, what we are having is this kind of architectures, right? So this was the first architecture, very similar to the LeNet architecture, having lot of different you can say layers are different. If you look at both the architectures, the layers are different. There are a few concepts they have incorporated, like data augmentations, ReLU activation function, and there are so many concepts they have introduced over here, how to use dropout and all, right? And if you just look at this architecture again, this in the first again it takes some input followed by some of the convolutional layer. At the end, there are also some FC layers containing 4096 neurons, 4096 neurons, and the last layer contains 1000 neurons. What does it mean? That it was basically trained on a data set having 1000 number of classes, right? And which is ImageNet data set. And ImageNet data set plays very important role, I mean, for the evolution of the CNN architectures. And Professor Hinton also recently been awarded as Nobel Prize. So because of its lot of contributions, it is the only one contributions, right? Towards the CNN architecture, but he has also developed backpropagation algorithm, capsule network, and so many other different types of architectures. But yeah, here is the list of popular CNN architectures which was developed over the years from 1998 to 2022, right? So there are a couple of so many other architectures you will find, but here are the list of the most widely used architectures, even widely used, right, via transfer learning. I will discuss later on. So it's all started with LeNet, then followed by AlexNet in 2012, then followed by VGG. VGG, I mean, there are two variants of VGG, 16 and 19. So it was published in the year 2014, followed by GoogleNet, ResNet, DenseNet, MobileNet, EfficientNet, and ConvNext in 2022 in a CVPR paper. So all these papers have been published in top tier conferences. And most of the architectures, right, initially was published by the academicians, and later most of these architectures have been developed by the industry peoples, right? So it is just I mean, it's not like that only academicians have proposed this. So even the industry people have also contributed towards the design of the convolutional neural network architectures. So now the question is, if AlexNet was there, so what is the need of VGGNet? What is the need of GoogleNet? Right? So there must be something right new into it. So that's why people are using, or else all the convolutional neural network will look very similar. So there are a couple of connections. I mean, the idea was something very different in AlexNet. If you go through the architecture in the first layer itself, right, the authors have basically not mentioned why they have used 11 cross 11 filter at the first layer. Right? Maybe that was the idea, that let us first apply a higher size filter and then slowly we reduce the filter size like that. But in the VGG net, so basically the developers have mentioned that no need to use high size or you can large size filters. So instead of that, what you can do is you can simply use 3 cross 3 filters sequentially for 2 times to have the same impact of 5 cross 5 filter. So if you just continue 3 cross 3 filter for 3 times, so it will also give the same impact of 7 cross 7 filters. I hope you are trying You're understanding my point, right? So instead of applying the larger filters, so you can just apply 3x3 filter to gain the same impact with lesser number of parameters. How is it possible? So basically, when I say number of parameters in a convolutional neural network, it is not like the parameters which are only involved in the last layers, like the dense layers. Those are also involved in the convolution operations, like the filter coefficients. The filter coefficients, we do not have any idea about the filter coefficients. We are initializing it randomly, like we are initializing the weights and biases in case of traditional neural network, right? So we have a lot of filters. So those filter coefficients, right, or filter values are nothing but weights for us, and every filter is associated with a bias, right? So the idea was if you are using a 3x3 filter, so the number of parameters is going to be 9. I'm considering only a two-dimensional filter, right? And if you are choosing, let's say, a 5x5 filter, so then the number of parameters is going to be 25, right? So what I'm saying that if you are using 3x3 filter, it will also cover the same receptive size field of size having size 5x5. So 3x3 filter, it is 9 plus 9 equal to 18 number of parameters. But if you are directly using a 5x5 filter, so it will lead to 25 parameters, right? So similarly, if you are continuing 3x3 filters or applying 3x3 filters 3 times, so you'll be having 27 number of parameters. And if you are choosing 7x7 as a filter size, so then it will be totally 49 parameters. So you see how the number of parameters is going to be less if you are choosing 3x3 filters instead of a larger size filters. In addition to that, there are benefits of going deeper and deeper, right? Because it also improves the nonlinearity in the network, right? So that was the idea behind the VGGNet. Although that idea was pretty good, but they could not actually end up with less number of parameters compared to AlexNet. The AlexNet was containing around 60 million parameters, but the VGG was around 138 million because of the usage of the 3 layers or 3 fully connected layers at the end, right? So although the idea was good. Again, GoogleNet, they come up with new ideas. Why not to apply multiple filters at a time, right? Multiple filters means we are only applying 3x3 filter at a time. So why not to apply 3x3, 5x5, or even 1x1 or 7x7 like that? So what is the benefit of using multiple filters? Filters with different size, basically, right, at a time or simultaneously. Yes, it gives us or it helps us in analyzing the features at different scales, right? It is very, very important even in the medical imaging domain. Why? Because we do not know whether the regions or the 2 mm regions are of which size. So if they are of different sizes, so you can just use the multi-scaling. Basically you can extract the features at different scales, and that is what is known as multi-scale feature extraction properties of a network, right? So similarly, you will also find some different intuitive. Of course, the intuition is different, right, for each of the architecture, right? If you just go through the ResNet paper, or what you will find is there is a residual connection that the developers have proposed, and they've also explained the importance of these residual connections, how it avoids the problem of vanishing gradient, right, and how it basically helps in better feature flow, basically, right, in the network. If you want to have a better feature flow in the network, so this kind of architecture or this kind of residual connection, sometimes known as keep connection, is very, very useful. So similarly, people have also tried to design some lighter architectures like MobileNet to deploy the architecture on edge devices like mobile devices, right? So if you just go through the literature, you will find different kind of concepts that has been introduced over the years into the convolutional neural network to enhance its capability for solving complex problems or complex image or computer vision problems, basically. And these are such architectures which are nothing but the winner of a particular challenge known as ILS VRC, and which was started in the year 2010. We all know about the challenge. It is like just a hackathon where the organizers will release the train set, and your task is to design the model, submit the model to the organizer. The organizer will test your model, the model of all the participants, and then they finally declare the winners. And these are nothing but the winners of such a challenge. right? And even in 2010 and 11, so the winners were like using shallow architectures. But in 2012, when AlexNet came in the picture, so it was just an 8-layer architecture. So when I say 8-layer, means there are only 8 learnable layers, right? I mean 5 convolutional layers and 3 densely connected layers, right? Now you can just see, I mean, why actually AlexNet was becoming very popular at that time, because this challenge was like, is a very interesting challenge. If you just go through it, is not only consisting of only one type of problem, but also different types of problems like object detection, segmentation, or like that. And classification is one among them. And here is the result of the summary of the classification, right? The performance, or basically the error rate, right? What I'm trying to show you is the error rate here, right? These bars are nothing but showing the error rate of different models, right? So if you just look at the error rate of AlexNet, is 16.4, and it was earlier 25.8. So there's a drastic, change. I mean, you can say reduction in the error rate values, right, from 25.8 to 16.8. So then people thought about, hey, what is this convolutional neural network? How can it gives a better performance? And then slowly people have just modified, introduced some new concept, as I mentioned. And then you can also see a trend over here that when the error rate was 16.4, it was 8 layers, and the error rate was 7.3, 6.7, and the number of layers is going to be very high later on, right? In ResNet, it is 50, 101, like that, right? So is it, I mean, the trend, like if you just increase the number of layer, the error rate is also going to be very less. So, I mean, whether always deeper is the better, is it that simple to conclude here that yes, deeper is the better? Can I conclude like this? So those who have already worked on this particular field, they can better comment on it, right? So I'll show you some interesting things. I mean, I'll just ask you this question. So is deeper is always the better? In traditional neural network also, we know that deeper is not always the better, right? Because the model is going to be complex. But here can I say that deeper is the better? Because what I've seen from this trend, right? Yes, the deeper is better. I mean, the deeper is the deeper architecture is leading to a smaller error rate. So is it the current trend? I mean, can I conclude like this? So have you seen, or have you done any experiments, right? I mean, just by adding more number of layers into a convolutional neural network is always leading to a better result or not? So let me check. So any comment on this? Yeah, we will discuss. We will discuss the queries, right? If you're having any queries, we will discuss definitely. Yeah, so my question is something very different here. My question is, if we go deeper and deeper, that means if we add more number of layers into the convolutional neural network, will it always give us better result? And not like that, actually. So there was an experiment, and the results also you will find in the ResNet paper. So from where I've collected this graph. So it basically tells us this is a graph between iteration versus error, right? Here there is an 18, I mean the performance of the comparison has been made between two convolutional neural networks. One is 18-layer convolutional neural network, and one is 34-layer convolutional neural network. Right. So now you see the 18-layer convolutional neural network is having better error rate compared to the 34-layer. So that means 18-layer is better than 34-layer. So you are having even more, 16 more layers, right, in a convolutional neural network, but the result is not good. But so what they claimed that with the introduction of the skip connections, right, they got some interesting results, right? What was that? So now this 18-layer architecture, the 34-layer architecture is giving better error rate compared to the 18-layer architecture just by using the skip connection in between the layers. Right, so you have to, if you want, you can just go through what do you mean by the skip connection or residual connections, right? And how, why it is important and how it helps in solving this type of problems, right? It's just not, that means it is not always true that deeper is better, right? We need to be very careful that whether we need to include more number of layers or not. Fine. So now let us talk about, right? So there are even, if you go through the literature, you will also find several other types of convolutional neural network models available, right? But these are some of the, you can say, very popularly used convolutional neural network with some different concepts, designed. So limitations of working with convolutional neural network, there are also a few limitations when we work with convolutional neural networks. What are those? Like you might have seen while implementing convolutional neural network, you need a lot of hyperparameters and you need to carefully choose all those hyperparameters, right? So we need always a hyperparameter tuning and optimization, basically, right? Of the parameters, which is always in terms of millions, right? It's very, very difficult because it is really, really a tough task, right? And as I mentioned, that hyperparameter tuning is very, very important, like how to choose the learning rate and how to choose the optimizer, how to choose the batch size, so, right? So every hyperparameter plays a very, very important role, right? And it greatly influences the output, or you can say the results, right? So you have to be carefully choose all those hyperparameters. It's always a concern, right, while designing the convolutional neural network. So at the same time, there is a high possibility that the convolutional neural network may suffer from overfitting issue because of the limited data which we are having, limited level data which we are having compared to the number of parameters, right? Because the number of parameters, as I mentioned, right, are nothing but in terms of millions, right? Sometimes it is 60 million, sometimes it is 130 million in case of BGG and all. So if you are having less number of samples and a high number of parameters or huge number of parameters, so there's a possibility that your model may suffer from overfitting issue. And you know that once your model is suffering from overfitting issue, it is your model may not generalize well and may not perform well on the on-scene data. And this kind of convolutional neural network require a long time and computational power to train. Yes, it is of course true. So you can see the results, some of the results over here, like the popular models, AlexNet, VGGNet, Inception, basically proposed by the Google, and the ResNet having more than 23 million. Sometimes it is 25 million. Sometimes it is 60 million, even beyond that. And if you look at the time required to train the AlexNet model on two GTX 583 GB GPU models, it was taking like 5 to 6 days to train the AlexNet model. Similarly, 2 to 3 weeks to train a BGG model on 4 NVIDIA Titan Black GPU, right? And for Inception, although it was mentioned that it takes 1 week of time, but the hardware was not exactly mentioned in their paper. So that was the actually, idea behind it. So whenever we are using convolutional neural network, we need to take care of all these things, right? So how to avoid this type of things? How to deal with this type of issues? So there are a couple of strategies which we are adopting nowadays to address these challenges to some extent. And instead of taking the random initializations of the filter values, basically the weights and biases, can we have something called as initialization process or better initialization process? Yes, there are initializations process like he and Clorot, so which will help us. If you just go through their paper, and even we have also empirically seen that in some cases this kind of initialization is giving better results compared to the random initializations, right? And hand designed or handcrafted, what does it mean? That instead of taking the random values of the or random filters, basically, so what we can do is we can initially take the filters like age based filter or shape based features, right, with certain orientations. Then that will help us. If you are having some knowledge on the problem domain, so you can just come up with such kind of filters, and those kind of filters you can initially apply. In place of taking the random filter value, so you can just take those type of edges or edge based filters or some shape based filters for the convolution operations. So that may also help you to some extent. There are also a couple of papers which you'll find in the literature where they have shown that yes, if they started with some this kind of filters, so they're ending up with some good results compared to the traditional approach. Like the random initializations. And people have also chosen some of the layers intentionally to get the features and to train them starting from the initial layer to some of the layers, right? But this is not a common practice, right? In convolutional neural network, we don't want to manually go to the particular layer and train the model and like that. And there are some regularization methods which you might have come across while studying this kind of machine learning as well, right? And deep learning. So like L2 weight decay, L1 weight decay, dropout, batch normalization is very, very important things, including data augmentation, right? Which helps us in reducing the overfitting issues as well, right? So now the question is, these are some of the ways how to deal with the problems which we discussed here, right? To some extent, as I mentioned, but how to completely or how to even think of designing some sort of convolutional neural network to better address all those challenges, right? So before I discuss what do you mean by transfer learning and all, let me also show you the interesting property of a convolutional neural network, which you might have seen in some of the other lectures. That convolutional neural networks always learns the features hierarchically. That means it gives us low level features, middle level features, and high level features. So these low level features are like edges, its different orientations, color blobs, and so many others. And it remains constant across various models, right? So these are very common kind of features we basically all the CNN used to learn, right? And this will work on all possible types of data, whether it is a natural image, whether it's a medical image, right? Always we need this type of features, right? So these are like generic features, we can call simple and generic features. But when you go deeper and deeper, so you will get to learn middle level features, which are nothing but sometimes combinations of the edges, color blobs, right? And the high level features, if you look at, these are very specialized features, and these are not generic features. These are data specific, right? So these are not generic, these are data specific, and these are like abstract and very specialized features, right? So this is very, very important to understand that it gives us, you can say high level features, low level features, or hierarchical features, right? And then which of the features are generic, which of these features are specific to the problem statement or specific to the data. It is very, very important for us to remember. Why? Because this transfer learning somewhat depends on this, and you will definitely tell me the answer if I ask you some questions of the transfer learning. So whether, how to fine tune the model, right? So this slide is going to be very, very useful, right, to understand the concept of transfer learning and basically the different strategies in the transfer learning, right? So transfer learning is one of the most important concept which many of the researchers are currently adapting to solve some of the problems, and we'll see what do you mean by transfer learning and what are the other ways to also use convolutional neural network for solving medical image analysis task, right? So if I compare this transfer learning with the traditional learning process, so in the traditional learning, will be given different data sets, right? Let's say different tasks, and we are designing different systems for it, right? But in case of transfer learning, so what we usually do, so we'll be given a set of source task, right? The domain, and your task is to gain the knowledge from the source domain, and to use the target domain data, right, as well as the knowledge from the source task, and then we will design the model. Basically what we're trying to do here is we are transforming the knowledge from one model to another to solve a similar type of task, right? So if to solve a similar type of task, we'll see once again, right? So what do you mean by this transfer learning? And also we'll see some of the scenario where transfer learning can be applied. Basically, so transfer learning is using the knowledge learned over different tasks, having sufficient data, of course, to add the training of the current task. And this will help us. The transfer learning will help us, and it will not require much amount of data compared to the traditional learning process. In the traditional learning process, we usually learn the model from the data only, or learn the model using the data which is given to us, right? So we don't have any knowledge. So only you'll be given a set of images and you will design a model from the scratch. However, this kind of approach, right, always demands a huge amount of data, right? And but if you are using this transfer learning concept, because you are using the knowledge of a pre-trained model, a model which has already been trained on a large source task, and you are trying to use the same model for solving a similar type of task, right? So what does it mean? Let's say somebody has designed AlexNet for solving natural image classification problem. Now your question is, what do you mean by transfer learning? So can I use this AlexNet architecture to solve a brain tumor classification problem? Right? If I can use the AlexNet to solve, the AlexNet has already been trained on a different task, that is the source task, right? So now with the knowledge, that means the model has already been trained. And now I want to use this AlexNet, which has already been trained on a source data set, right? I want to use this AlexNet to solve my problem. So now what are the different strategies we have to adopt this kind of architecture or AlexNet to solve the downstream task, right? So this will definitely, help us in reducing the time required for training, as well as, it will demand less number of hyperparameter tuning, and it will also demand less amount of computational resources compared to the first strategy which we discussed, that is training from the scratch, right? And when I say the model has already been trained on large data set, right? Or model has been already trained on some source task. So there are different ways to, or you can say there are different strategies to use the model, right? So what are those? Either you can initialize, or either you can initialize the parameters of the last layer, and you can fine tune them, and the rest of the network will be frozen. I will discuss about it in detail later on. And what you can do sometimes, if you want, you can use those pre-trained weights. When I say pre-trained, the model was already trained, right? And you can directly use those weights, those optimized weights, right, as the initialization, which is a good initialization rather than random initialization. So that means you are starting your training process from a good point, right? Or sometimes if you want, you can retrain the model, retrain the entire network and retrain some of the layers. We'll see in which scenario you have to train the entire network, in which scenario you have to train some of the layers, right? We'll see. So the choice, right, that we have discussed about 2-3 different types of possibilities here, how to retrain the model, right? In which scenario? So scenario I have not yet mentioned, I will mention. So basically the choice depends on various factors such as the dataset size and the similarity of the target and source dataset, which is very, very important, right? We'll discuss one by one. So now let us first discuss the strategy where the dataset, or the scenario where the dataset is small and the target and the source datasets are similar. I hope you are getting my point. You are dealing with a very small dataset, and your target domain and source domain is pretty similar, right? That means the source domain on which the model was trained and the target domain on which you are planning to deploy your model or you are planning to train your model are pretty similar, right? So if this is the scenario, then what you can do, and the data set is also small, what you can do is you can only randomly initialize the last layer, and you can freeze the other layers. Because what about the other layers? The starting layers or the initial layers gives us generic features, and the end layers gives us the special features, right? And if the target domain and source domain are same, maybe the special features are also useful. Always the generic features are useful, we know that. And the special features are also be the same for both the domains, because both the domains are same, right? And in that case, what you can do is only you can fine tune the last layer. So how would you do that? Let's say your friend has designed a model, right, for solving, brain tumor classification problem, or let's say brain disease classification problem, right? And you now want to solve a brain tumor grading problems. Maybe the previous problem which your friend has solved was a 10 class classification problem, that is the different types of brain diseases, right? And now you are solving a similar type of problem, right? Maybe you can consider also CT scan as well, right? In place of, let's say, MRI image, let's say you are considering a similar type of problem, right? And your data is something different, right? And let's say the target and source data sets are pretty similar. That means your friend has designed a model for solving brain disease classification problem. And now you are trying to solve a similar type of problem, which is a brain tumor grading problems. So where you want to assign the brain tumors either into grade 1, grade 2, grade 3, or grade 4. It's a 4 class classification problem. And earlier it was a 10 class classification problem. And let's say the input to both the models are nothing but brain MRI images, right? And the kind of features, right, the previous network has learned, right? I mean, that was designed by a friend, right? contains obviously some generic features, some specialized features, and what you are expecting that those type of features may be helpful for me to solve the problem, right? And the data set is very, very small in your case. So what you can do is only you will go and you will replace. Look at this one. Let's say this is my architecture. I'm considering again a very simple architecture like VCCNet, or you can say AlexNet, right? It's a very simple architecture. So what you will do is you will simply replace the last layer with a new layer. What does it mean? So earlier the last layer was containing 10 neurons for solving 10 class classification problem, and now it has become a 4 class classification problem. So what you will do? So you have to replace this layer with a new layer with only 4 neurons. And the C is nothing but, let's say, the number of layers or the number of neurons in the target domain. Fine. And now you have to reinitialize this, of course, and train the model. And now you can also see another thing here. I'm freezing all the rest layers. That means I'm not updating or fine tuning the weights and the biases that are involved in other layers. Only I'm fine tuning the last layer. And when it is possible, when the data set is small and the target and source data sets are pretty similar. I hope to make some sense. Well, now let's say the data set is small, but the target and source data sets are dissimilar. If the model was designed on natural images, let's say, for example, and now you are trying to use the same model, right? Let's say with the help of the model was trained on natural images, and your goal is to use the same model via transfer learning to solve a medical image analysis task. So we don't know whether the specialized features, right, is going to be useful for us or not. So what do you think? The specialized features, basically the features, right, at the last layers are going to be useful for us or not? And what should you do? Yes. Any comment on this? The data set is small, but the target and source data sets are dissimilar. That means you cannot directly use, right, the specialized features or the features at the final layers, which are very specific and very abstract and data dependent as well. So then how can we solve the problem? The simplest way actually to solve the problem. Yeah, they might not be useful. Okay. Yeah. So that is why what you can do here is we can simply extract the features. In this case, what we can do is we can simply extract the features only from the generic layers, right? And then those features can be passed directly to any classifiers, right? If it is either it can be a super vector machine, it can be any classifier, machine learning based classifiers. You can do that. That's a very common practice when the data set is very small. The target and the source domains are also dissimilar. So what you can do is you can simply extract the features only from the generic layers, because what do we know that generic features will help us in at least extracting some of the important features based on shape, edges, colors, and like that, right? And those features may be helpful sometimes, but this kind of approach or strategy may not give you always the optimal results, or you can say, good results, right? But you can, if you don't have, data set, a larger data set, what you can do is you can just follow this procedure. Fine. Okay, so the third one, I think, okay, is mistakenly written is this one. So the data set is large, right? So we don't know whether the target data set and the source data sets are similar, dissimilar, doesn't matter. Whether this is actually, I've wrongly written. So it is actually data set is large. When the data set is large, what you can do? So when the data set is large, so what you can do is we can fine tune either the whole network, right? Or what you can do, you can fine tune some of the layers, right? It all depends, right? So if the data set is large, what you can do is either you can fine tune all the layers, See, the last layer you have to replace based on the number of, based on, I mean, if you want to solve a classification problem with different number of classes, so the last layer you have to change, you have to reinitialize it, but the other layers can be fine tuned, right? In place of freezing all the layers, what you can do, you can fine tune all the layers because you are having sufficient amount of data, right? So sometimes, and if you go through the literature, you will find, let's say the target and source data sets are a bit different. Then in that case, what you will do? The data set is large, right? You are having a large data set, and you can just use the pre-trained network as a good general, I mean, good initialization point. That also you can do, and you can fine tune the model, either few layers or all the model, the whole network as well. Not a problem. Right, but while fine tuning, you need to keep in your mind that yes, the learning rate has to be kept a little bit low, right? Or else it will be difficult. Fine. So if the data set is different, in that case, I mean, the target and source data sets are very different. I mean, they're completely different, let's say. So what you can do is either you can just go for training the model from the scratch, or you can follow some of the techniques like transitive transfer learning, right? You can just go through the literature and check what do you mean by this transitive transfer learning. So where will be an intermediate step of transfer learning, right? There will be one source domain, there will be one target domain, and there will be one intermediate domain, right? Which will be helpful. Or maybe you will find some of the variants of those kind of transfer learning process, right? If the data set is completely different from this and this, and if you are sure that the kind of features, right, the model, the pre-trained model has already been learned, is not going to be useful anymore. So then you can just follow this type of procedure. So you'll also find some of the papers based on transitive learning and some of your subsectors. Fine, but this is the scenario where data set is large. Fine. So that's what I mentioned over here. You can see, right, that if you are having smaller data set, so then you can just reinitialize it, right? I'm in the last layer, and you can just freeze all the other layers. And if the data set is bigger, either you can train some of the layers, or you can train, right? Or you can train means you can fine tune, right? We call it as a fine tuning because you are retraining. The weights have already been optimized, right? And now you are simply fine tuning or readjusting the weights by putting different learning rates and all, right? Sometimes people used to also apply 2 stages of learning where they used to train the last layer, right? They train the last layer with some learning rate and train other layers with some other, with some other learning rate, right? So either you can train some of the layers, or you can train, or you can fine tune all the layers of the model if you are having a larger data set. That's up to you, and that you need to check how many layers we need to fine tune, right? So if I summarize that, what are the different ways to use convolutional neural network for medical image analysis? It is just training from the scratch. As I mentioned, like AlexNet, you will design your own architecture and you will train. That means you will initialize all the parameters randomly, and then you will backpropagate the error, and then you will optimize the weights, right? Using some of the optimizers like SGD or ADAM or maybe RMS prop and maybe some other other algorithms, right? So the second one is transfer learning, and we have seen there are a couple of strategies in case of transfer learning which can be adapted, and it is dependent on the data set size as well as whether the source domain and target domain is different or same. Right. And the last one is the last one which we also discussed, right? When the data set is small and the source and target domains are similar, you can just go for the last one, which is using off-the-shelf return CNN feature. That means you will use this convolutional neural network as a feature extraction technique, and then you pass those features into a machine learning classifier, which is pretty similar to the machine learning based system which we have seen earlier, where you are applying some of the feature extraction technique to extract the features, store the features in a feature vector, then passing the features into a machine learning classifier, right? Fine. But there are several things which, you can say takeaways here, like the training from the scratch. The first approach here, although it's more accurate, but requires a lot of images, right, to effectively train the model. And the transfer learning comparatively requires less amount of data, fewer computational resources, and the last approach, even if you are having, let's say, very small number of images, even less than 50, you can say. So you can also go for the last one. The last one is not, I mean, you may not expect always good results from the last approach. Why? Because there is nothing called learning happening here, right? You are not doing any learning. So what you are doing, you are only passing the images to a pre-trained architecture and extracting the features from the generic layers. And then you are passing those features to a traditional convolution machine learning classifier. That means we are not training, or we are not fine tuning the model, right? So the model has not seen the images of the target domain, and we are simply passing the images of the target domain and extracting the features. It is like a feature extraction, like handcrafted feature extraction, right? Which you have seen in case of traditional machine learning. Fine. So, and another important aspect here is how to design the lightweight models. If you are if you are planning to adopt the first approach here, that is training from the scratch, you cannot uh, design a conventional neural network with so many parameters, like VGGNet having 130 million parameters, right? Because what we know that the number of parameters is very high compared to the number of images. So what we can think of is, we can think of designing a lightweight models having very less number of parameters, and the number of operations is going to be very less in that case, right? So how to design the lightweight models? So that is what is also, one of the concerns at that time. So people have come up with a lot of ideas, lot of lightweight models like MobileNet and several others. And they have also shown that with less number of parameters, with comparatively less number of parameters, the accuracy they have achieved was really very promising, right? So we'll also see some of the lightweight models which we have developed, right, for solving some of the tasks, medical imaging tasks, and what was the goal behind this, and how did we reduce the number of parameters, right, without compromising the performance. Also, we'll see that. So coming to another problem statement, right? I mean, just now we've talked about classification. So what does, what do you mean by this segmentation, right? How it is different, and is there any possibility that we can use convolutional neural network to solve segmentation problem, right? So classification is very simple. So given a set of images, at the end you are getting some of the probability values from the convolutional neural network, and based on the highest probability value, you are just assigning a label. And we have talked about it in the first hands-on session, that from the probability value, how we are getting the levels, the class levels, right? And how we are also calculating the loss function or the loss, right? So in case of segmentation, the output is also an image. Input is of course an image. The output is also an image, right? So segmentation, when I say segmentation, it is nothing but partitioning the images into multiple segments. Right, it has a lot of applications in several fields of convolution, several fields of computer vision, including medical image analysis. Right, so if you look at the one of the results, right, this is the input image, right? So here is an example of semantic segmentation, basically, which can be casted as a pixel-wise classification problem, right? So this kind of problem, which we have seen in the last class or in the first hands-on session, can be also solved using k-means clustering. But we know that what are the problems which we always face in k-means clustering. So now we're interested in solving similar type of problem with the help of a learning-based approach. And of course, a learning-based deep learning approach. And when I say deep learning and working with images, so our first choice would be convolutional neural network. So we'll see how this convolutional neural network is going to help us in solving semantic segmentation problem. So here is an example you can see, right? And then if you look at this image, and this is the output, right? How we segmented that image into particularly three parts. One is bicycle, one is person, and one is background, right? So that means I can consider this problem as a pixel level classification problem. So previously we were classifying an image and providing a label to a particular image. So now we are classifying the pixel. So that means classification is happening at the pixel level. So previously the classification was happening at the image level, right? So what does it mean? That means every pixel will be classified either into person category or into bicycle category or into background category. So now, so what are the procedures to be followed to classify each pixels either of these three categories? right? But for this, what we need is a ground truth image or a pixel level annotations. That is what we require, which is very, very difficult. Pixel level annotation is even more difficult compared to the image level annotation. I hope it makes some sense, right? Because you have to annotate the image at the pixel level, which is a time consuming task, even tedious. And looking at the image, assigning a label is very, very easy, right? So now we have just now casted this segmentation problem into a pixel level classification problem where our goal is to classify all the pixels into different categories. It all depends upon the kind of problem which you are solving. Let's say a medical image is given to you and your task, a medical image is given to you and your task is to only highlight, let's say, the blood vessels in the retinal fundus image. So then your task is to classify every pixel either into two categories, whether it belongs to this retinal vessel category or to the background, right? So most of the cases in medical imaging, so the number of classes are two, but there are some cases even the number of classes are more, right? So it's not always two. It can be even more than two, more than three, more than five, even more than five, even in case of medical imaging. Fine. So as I mentioned, although these learning-based segmentation methods are more accurate compared to the traditional approaches like k-means clustering, thresholding, graph code algorithms, and there are several other algorithms available for image segmentation. But this is, although it is more accurate, it is quite annotation intensive. It always requires pixel level annotations. But still, we are interested in solving the problems because of its because it is highly accurate and it gives interesting results, even sometimes beats the human beings, even the clinicians as well. Here is again the evolution of the segmentation, CNN-based segmentation models like I have shown you in case of convolutional neural network for solving classification problem. We were having a LeNet followed by AlexNet and then BGG, GoogleNet, ResNet. So similarly, you will also find the evolution of the convolutional neural network for solving segmentation problem. This was the first architecture which was proposed in 2014, the fully convolutional network, right, for solving semantic segmentation problem, which is a pixel level classification problem. So similarly, the most famous architecture is UNet architecture, right? Till date, the most popular architecture, and this was the only architecture which was proposed and validated first on the medical data and then later been adapted to other image processing and computer vision tasks. And this was published in a MICAI conference. I think you might have heard about this conference name several times, right, by a lot of the speakers. So MICAI is one of the top conference in the field of medical imaging. Fine. So similarly, you will find a lot of variants of UNet architectures by introducing the residual connections, dense connections into the UNet architecture, by introducing attention mechanisms into it, and there are several other variants, right? I mean, you will also find some of the transformer variant of UNet architecture known as TransUNet, SwinUNet, DS TransUNet, and all. And most of the architecture, if you look at, many of the architectures have been validated initially on the medical imaging dataset, right? So this is the first architecture, the segmentation architecture, you can say, semantic segmentation based CNN architecture. And if you look at this architecture, it looks pretty similar to the VGGNet architecture because it adopts the VGGNet architecture, right, initially. And then finally, it basically removes the fully connected layer, the final fully convolutional layer, and it is replaced by a 1x1 convolutional layer and followed by an upsampling layer, right? And that particular upsampling layer will help us in upsampling those feature map into a size similar to the input image size, because ultimately our goal is to generate the image at the output end, right? That means the output is an image. The output is not basically a class label here, right? Or a single probability value. The output is an image here. So how would you get that? So that's why we need some top upsampling even after a lot of downsampling, right? So they've adapted VGGNet initially, and then later they have removed the last fully connected layer, right, which was containing 1,000 neurons, if you remember, and they replaced with a 1x1 convolutional layer with C plus one number of classes. And I mean, this fully convolutional neural network was designed to solve a 21 class 21 class segmentation problem, including the background. There were 20 classes, and one is for background. So there will be 21 number of classes. That means every pixel will be classified into 21 pixels, right? So I mean, the last layer, basically the last layer, if you look at this architecture carefully, the last layer contains C plus one number of filters, right? 1x1 convolutional filters. Basically, C plus number of the number of classes are 21, so they have included 21 number of filters to get and feature map having depth 21. So when I say the depth is 21, that means for every pixels you will be getting different values, right? And then you can just apply submax over it, and then you can apply the cross entropy loss function over it to compute the loss. But the cross entropy loss has to be computed pixel wise once again, right? So I have already mentioned, I will also talk about the same thing in my hands-on session, that how can we do it, right? So one thing only we need to remember, because this traditional convolutional neural network helps in reducing the size. So that means we need some sort of, upsampling operations at the end to upsample the feature map, right? And to get back the original image size at the end. And this was the idea, but they have only used one upsampling layer to get the output. And this was also the limitations of this architecture, you can say. And later people have proposed some encoder decoder based architectures like SegNet. And if you look at this architecture, it looks very good. I mean, compared to the previous one, because this is the encoder part, this is the decoder part, which is just a mirror. The decoder part is just the mirror version of this encoder part. So the way you have reduced the feature maps, the similar way you will also upsample the feature map, right, in the decoder end. But during upsampling, right, they have not used any. I mean, they have basically during downsampling using pooling, they have kept the record of the indices, basically the pooling indices, and they have used those pooling indices to get back or to upsample the images of the same size. Fine. And finally, they are using a 1x1 convolutional layer at the end, equal to the number of classes, and the number of filters will be equal to number of classes, so that the depth will be equal to number of classes. You will get, let's say, C plus one number of values for each of the pixel. Fine. But in case of this fully convolutional neural network, I forgot to mention one important thing here, that how to upsample. There are various upsampling operations we are having, right? You might have heard about something called as interpolation operation, right? So there are various upsampling operations we have in image processing. If you go through the literature, you will find it out. But what they have proposed is, not to use any interpolation based techniques, but to use an interesting concept, which is known as you can say transpose convolution or op convolution. So if you look at the theory of this convolution, so whenever we are applying a filter, let's say having size 3x3 over a image, so after convolution, the image size gets reduced to a bit, and it is dependent on the the size of the filter. So this upsampling or this op convolution or this transpose convolution is just the reverse one. That means it will help us in enlarging the size of the feature map after applying op convolution or sometimes transpose convolution. And people are sometimes also using the term deconvolution, but which is not true. So deconvolution has some different meanings in the signal processing. So transpose convolution and op convolution helps us in increasing the size after applying the convolution operation. But the traditional convolution helps us in reducing the size. But if you're choosing the padding operation, then you will get the same size output, right? So this is the architecture which I was talking about, right? The most popular, the people are still using this concept, right? This unit architecture, the name itself says that the architecture, right, looks like English letter U. If you look at here, so this architecture also contains some encoder part and decoder part, but there is one interesting connection which we'll find from encoder to decoder, also known as the skip connection. And these connections are very, very important here. And this will help us in preserving the spatial informations, right, from the encoder end to the decoder end. And with this skip connection and the encoder and decoder architecture, in this encoder architecture is pretty simple, similar to the convolutional neural architecture which we have seen, let's say AlexNet, ResNet, it can be DenseNet, anything. And at the other end, they have used transpose convolutions, right? Applied transpose convolutions to increase the size. And also they are taking the informations from the encoder end and they are concatenating them together, right? They're fusing them together and sending it to the next layer of the decoder. And finally, they're ending up with and the image size having 256 cross 256. Let's say the input image size is 256 cross 256, and what you will be getting, as I mentioned, let's say it is a two-class classification problem, basically two-class segmentation problem or pixel level classification problem. What you can do is every pixel will be classified either into class 1 or class 2, basically whether it belongs to the tumor or it belongs to the background, right? And based on that, you can just apply either you can, because it's a two-class classification problem, you can either use sigmoid, either use submax, right? Compute the loss function and then compute the loss values. Then you have to follow the same procedure. Even the transform learning can be applied, as I mentioned over here. The transform learning can be applied to solve image segmentation problem the way we discussed. To solve the image classification problem in a similar way, you can also adapt the pre-trained the pre-trained segmentation models to solve, right? To solve a new type of segmentation problem. And again, it depends on the data, as I mentioned, whether the data set is large, whether the data set is small, whether the source and the target domains are similar or are different like that. Right. So here are some of the case studies. As I mentioned, that we have designed some lightweight models, right? Maybe in the year 2018, 19, like that. So we have also designed and applied in some of the areas like chest CT scan image classification and all. So this is the first architecture which, I mean, this is architecture which I proposed, a lightweight architecture which I proposed along with my student, right? I think okay, Amok Joshi, who is also going to, I think, speak something in this particular FDP in one session, right? So how what was the idea behind designing this architecture was to design a multi-scale feature learning network which can learn the features at multiple scales, because the kind of lessons, if you look at right, if you go through the data set, you will find the lessons are of different sizes. So our goal was to capture the information at different scales, and at the same time the models would also be lightweight. So this was the actually the basic building block of this particular you can say architecture which we have proposed. Although it looks like a sequential one, it is not actually sequential because it contains MFL block, which is known as multi-scale feature learning block, right? And this is not a sequential one. So this is how actually the MFL block looks like, where you can see we have not chosen any filters having size 7 cross 7, 5 cross 5. Rather, we have used 3 cross 3 filters sequentially to have the same impact of 5 cross 5 and 7 cross 7. So ultimately, this particular block will help us in extracting the features at different scales of different receptive field size, like 3, 5, and 3 times it is 7, right? And ultimately we are using a 1 cross 1 filter here just to reduce the number of filters and as well as the number of parameters. And this is how the architecture looks like. If you just take the summary and you will get the architectures. It was a two-class classification problem. So at the end, we could have two number of neurons. We could have also one neuron if you are choosing sigmoid as an activation function. At that time, you need to choose binary cross entropy, but we have chosen submax. So we have chosen as well as we have chosen cross entropy. So this was the comparison with the very popular models we did. I mean, in terms of parameters, in terms of size, I think I forgot to add the number of flops, floating point operations as well. Right? If you look at the number of parameters, it is significantly low compared to the other models. And the size also required to store the model is also very, very less compared to others. And if you just look at the performance which we have achieved, is a little bit higher than the existing approaches, right? That was, I mean, the idea behind designing this. I mean, how did we come up with this kind of lightweight models, right? Fine. So, I mean, this was the heat map people were talking about. The grad came, right? So you might have seen in last two lectures right, by Professor Gorthi and Dr. Mahapatra, that they've mentioned about the importance of the explainability and the importance of this, GradCam or heat maps generated using GradCam. So, which basically mentions or tries to focus on right, the important parts which are or the important features, right, of the image. But if you look at this kind of image, I mean, there are still some issues. The model is not focused properly. It is sometimes focusing on some irrelevant parts. So what is the solution then? Right. So the solution is just to introduce an attention mechanism into the convolutional neural network, this kind of architecture, which will help us in emphasizing or focusing only on the important regions while suppressing the irrelevant ones. Right. So we'll see later on. Maybe there is one particular session dedicatedly designed for attention mechanism based methods, right? Very, very important in medical image analysis. And another work also we did, I think, in the year 2022 or 2021, right? I mean, the idea was also to design another another multi-scale feature extraction block, which looks pretty similar to dense block, but in dense block you will find a number of dense connections between all the layers, but the dense connections may create some redundancies in the network. So how to avoid those redundancies, that was the idea, with less number of parameters. And then also we have some global connections, I mean global dense connections among the blocks we did, and the name was so-called GDense MNet, right? The Global Dense Multiscale Feature Learning Network. This was a paper which is accepted in 2022 International Joint Conference on Neural Network. So one of the renowned conference in the field of neural network. And the architecture, if you look at, and the number of parameters compared to the other models, traditional convolutional neural network, compared to that, it is pretty low. The number of parameters and the size and the performance also is also even better than the other models, right? And there are a few other things which I cannot cover. I think it is 6:27. So probably I will stop here and start the hands-on session quickly after 5 minutes, right? So if you are having any queries, so you can just ask, or you can just write in the chat box. I'll be happy to answer. And then we will yeah, I could see there are questions. Okay. What is meant by fine tuning some of the layers? Okay, so when I say fine tuning some of the layers, means I am not interested in fine tuning or readjusting the weights of all the layers, right? So let's say AlexNet is having 8 layers, I mean 8 learnable layers. So what I can do, so when I say fine tuning some of the layers, means I can only fine tune the last 3 layers or last 3 dense layers. So if I want, I can also fine tune the last 2 layers. That is fine tuning of some of the layers. That you need to check whether you need to fine tune all the layers. As we have discussed about the generic layers, the specific layers. So you need to check that which of the layers we need to train, or else you can just go for fine tuning all the layers, right? If you're having sufficient amount of data. I hope it makes some sense. Then there's another question. Please explain in depth, if less data is present, then how to train the model? I think that was we were discussing, right? I mean, if you are having less amount of data, you can also go for transfer learning, right? So, but while using transfer learning, there are various strategies, right? So either you can fine tune the last layer and check the result. And even if you want, you can just take, I mean, that all depends upon, again, the kind of data set which you are using and the kind of data set on which the pre-trained model was trained, right? So we discussed in detail that if the data, if the data set are similar, I mean, basically the source domain task and basically the source task and the target task, if it is same, right? So you can just go for only fine tuning the last layer, that may work, or else you may go for fine tuning some few layers. Or if it is dissimilar, then there is only one way. It's better to just of extract the features from the starting layers, or you can say the initial layers, and then you can just send the features to some of the classifiers. But that will be not end-to-end learnable, because you are again using some machine learning classifiers, which is dependent on the kind of features which you are extracting. Yeah. Any other questions? I hope. Yeah. How to get the masked images, sir? Any tool for masking? Uh, See, coming to basically, if you are dealing with medical images, then of course this mask images means this image. These are pixel level annotations, right? So this pixel level annotations will definitely be provided by the doctors. We can't do it manually because we don't have any idea, right, about the the presence of the tumor, the locations of the tumor, and even the shapes, the variations everywhere, right? So we don't have, that expertise to label or annotate the data. And once the annotation, yes, the doctor may just give us maybe the region. They can just give us the region, or sometimes the doctor used to give us the bounding box, right? So from that you can just create easily. You can create the mask. That is not an issue. But you need, this has to be done ultimately by the radiologist or by the clinicians, right? So how to think of variations to do in the existing work architecture so as to obtain improved results? If UNet is used for any medical image classification, would it perform better than other transparent? Okay. So it's a very good question, actually common question, sir. There are a lot of architectures which has already been available in the literature. So where to start with and what kind of novelty I should bring open, right? So into the network, so that the major problem is like nowadays is the reviewer is asking us where is the novelty in the architecture. So we have also used convolution, so we've also used pooling, so we have also seen these type of things in the architectures which was already available in the literature. So see, you have to go through the, as I mentioned, why I have shown you the evolution of the, CNN architecture, so unit, basically the segmentation architectures. So what people have done over the years. So that also you need to look at, right? And what basis, on what basis they have improved upon the network. So basically, let's say when I say unit, right, we have seen the importance of the residual connections in convolutional neural network, and then they've designed something called as residual network. So if you go through the architectures, basically that have been designed for solving image segmentation problem, you will find that people have also introduced residual connections into the unit architecture, and it is known as very very popular architecture known as a RES unit. And then people have introduced dense connections into unit, very similar to dense net architecture, and then they've called it as dense unit architecture. And they've proved on some of the data sets that dense unit is performing better than the traditional unit because it cannot capture the multiscale informations, it cannot capture, it cannot solve the vanishing gradient issues like that. So similarly, people have come up with some other ideas. You might have heard about something called as attention mechanisms, and they have incorporated attention mechanisms into the unit architecture, and the name of the architecture has become attention unit, just to focus only on the important parts and all right, and not to focus on other parts, because what is important for us to only focus on the important parts, because we want to only learn the features from the important parts. So similarly, then if you just go through the literature, you will find why people are doing this. Just to improve the results, right? Just to incorporate something into it, just to increase the representational power, the feature representational power, just to boost the representational power. That's what they're doing. And from where they got the idea? They got the idea from the literature. Yes, that with this many number of modifications, or with these modifications, if CNN is giving good result for some other applications, so why can't we adopt such type of things in basically in unit kind of architectures or segmentation based architectures, and people have done it, right? So in that way, you can also think of designing some new things, incorporate some new things. You have to identify how to, let's say we discussed the relevance of wavelet transform, let's say Fourier transform, I mean, we all know that, I mean, analyzing the images in the frequency domain gives us even more important informations, rather than spatial information. So people have combined analyzing the features of convolutional neural network in both frequency domain as well as spatial domain. We also did some of the works, right? So, I mean, how to just incorporate this frequency domain features into the convolutional neural network. That also we can do. So there are multiple things that you need to first identify, that what is the problem with the existing literature or the architecture of the existing literature, and based on that you can start thinking how to design the new architectures. And the simplest way is whenever people are also working on different learning paradigms, right? So instead of let's say using the pixel level annotations, can we directly apply, right? Can we solve the problem with the help of semi-supervised or weakly supervised techniques, right? Where only, let's say, bounding box is given, not the exact boundary of the tumor is given to you, because we know this is even more costly. The annotation is a bit costly. So let's say bounding box is given to us, and from the bounding box, how would you solve the problem, right? So that's what also you can do. I mean, using weakly supervised medical image segmentation problem. A lot of literature you will find on this, right? Any other questions? Okay. Oh, there are a lot of questions. So I have to answer quickly then. In which case, when can we say the trained CNN model is lightweight? Can we say when learnable parameters are less? Yes, of course. When the learnable parameters are less, I mean, in that way, we always call the model is a lightweight model. But it doesn't mean that I mean, it may so happen that if you make your model so lighter that it will not perform well on the test data, that means it will not perform well also on the trained data. That means your model may suffer from underfitting issue as well. So underfitting also may be one of the concern while you are making your model, even, I mean, making your model lighter and lighter, right? So that means you have to be very, very careful that even if you are making, let's say, a model pretty lighter, and your model is not performing well on the training itself, so then you will get to know about, yes, so that means I have to, I mean, my model is having very less number of parameters. So that is how we can also check whether your model, I mean, the model which you have chosen is the correct one or not, or you have to make some changes in the architecture. At the same time, I mean, sometimes of this, these explainable AI or interpretable AI models may also help us in checking the results whether my model is focusing on correctly or not, right? There are various ways to verify whether our model is performing well or not. Okay. What will be the approx size of the data set for disease diagnosis through ultrasound report? See, uh, it the what deep learning models demand, as you all know, that yes, the more you will pass the data, right, to the model, the more reliable result you can expect from the model. But if you are not having much amount of data, so you can just use those kind of foundation models on pre-trained model, right? You can just apply those, and there are also multiple techniques like I mean, nowadays, which are very, very popular, like knowledge distillation, right? So Professor Deepthi has also mentioned the same thing. So you can also use the knowledge distillation technique here, right? I mean, how to bring the knowledge of a large model to a small model to solve the problems, which can be easily deployed on some of the edge devices, right? That can also be done. So, I mean, people are also very much interested in designing these foundation models nowadays, so that anybody can use it. I mean, no need to train those kind of foundation models, because it takes a lot of time. So we can just adapt some of the important things from the model by designing a small model, I mean, which is sometimes known as student's model. There's a teacher student model concept in the knowledge distillation. You can just check it and you will get your answer. How can be overfitting avoided when training a CNN from the scratch on a small medical data set? Okay, so there are multiple ways to avoid, let's say, overfitting issues. The simplest one is I mean, just to use the early stopping criteria. I mean, I'll discuss it right in the hands-on session. I mean, why do we need a validation set here, right? So that's what the simplest way to check. And there are also a couple of other ways I mentioned also, like using dropout, there are some neurons which are not useful in taking the decisions. We can just drop them out. I mean, we're not removing them, we're keeping them in the network, but we are not considering they are outputs. Basically, at the same time, you can go for data augmentation, which will help you to some extent to avoid this overfitting issue. And there are a couple of other regularization technique also that also you can use. So what are the key considerations when choosing which layer of the pre-trained neurons to freeze versus retrain? Okay, so that's what we discussed, right? I mean, you need to look at the data set size as well as to look at the problem statement. I mean, the problem domain, whether it is similar with the source task or not. How does the choice impact on the performance? Of course, I mean, if you are not choosing it properly, if you are not training the model, let's say, if you are having a huge data set and you are simply training the last layer, right? So maybe I mean, if you are having a huge amount of data set, then you should fine tune more number of layers and readjust just to make sure that yes, my model has seen. I mean, my model parameters has been adjusted by looking at the images which I'm having with, right? So that also you can do. What techniques are used to make the CNN lightweight is a very interesting question. So I have just given one example of that. I mean, how to make the models lightweight. So there are a couple of ways to do that. So one is like the usage of the bottleneck layers, right? You might have heard about that is the 1x1 convolutional layer, which always helps in reducing the number of depth and also helps in reducing the number of parameters, and as well as avoid using large size filters. That will make your model, of course, lightweight, because here we're going to deal with a huge, huge number of filters having depth sometimes even more than 32, 64, 128, sometimes even more than 1000, right? And that will help you in greatly reducing the number of parameters. As I mentioned, the bottleneck layer is very, very important. At the same time, people have also applied different types of convolutions. They've not used only traditional convolutions. There are various types of convolutions. In addition to the traditional convolution, there are convolutions like dilated convolutions you might have heard about. I don't know. There are convolutions like depth-wise separable convolutions and separable convolutions. For example, let's say you are planning to apply a 5x5 filter over an image, and which is a two-dimensional filter. So I can just make it separable. I mean, if the kernel is separable, if the filter is separable, then I can apply a one-dimensional kernel in the horizontal direction having size 1x5. That is the kernel size or the filter size. And the filter size can also be 5x1 if I want to apply the same over vertical directions. So 1x5 filter and 5x1 filter can be applied together, right? And to have the same impact. That means if you are planning to use a 5x5 filter, instead of that, you can go for 1x5 filter and 5x1 filter, right? I mean, in both horizontal and vertical directions with less number of parameters. Now, previously it was 25. 5 into 5 is 25 number of parameters. And now it has become 5 plus 5, because there are only 5 parameters in the horizontal direction. There are only 5 parameters in the vertical filter. So it is 5 plus 5 equal to 10. Earlier it was 25 and now it is 10. Right. So that is how we can reduce. I mean, there are a couple of concepts, right? That has been proposed over the years through which you can make your model lightweight. So instead of applying traditional convolution, you can go for separable convolution. There is something called as a depth-wise convolution where filters will be applied at different depths. Right. So that will also help you in reducing the number of parameters, but that we need to check. So whether whether applying this separable convolution, there are also some conditions to be satisfied, right? So if that means this 1x5 and 5x5, if you just make them a product, basically it is an outer product, right? 5x1 into 1x5 will become 5x5, right? So the condition has to be satisfied, and this 5x5 has to be similar with the 5x5 which you are applying. Then only you are getting same answer, right? You will get same answers with less number of parameters. So this is just one of the examples I'm talking about, and you can choose any of them to make the model lightweight. Lightweight foundation models. Okay. For classification, you might have heard about something called as, mobile net is very, very popular. MobileNet is a very popular architecture, which is very lightweight. Even sometimes, I mean, if you go through the architecture and if you just summarize the architecture, you will find that it is less than, you know, 2 millions and like that. And sometimes even if you there are some variants even less than 1 million, right? MobileNet is very popular, even very popular in the domain of medical imaging because it is lightweight. And even if you are choosing BGGNet and AlexNet, and if you are just removing the last three layers, so this will also become, lighter. So GoogleNet was proposed when it was proposed. So the first version was only, having 5 million parameters like that, right? So there are also a couple of architectures which are lightweight in nature, but these mobile nets and are very popular for because of their lightweight architectures and all, right? So you can just go through that. There are also several other architectures which are taking less number of parameters. There are different variants, right? If you go through the architectures like DenseNet. So DenseNet is having a lot of variants. So DenseNet 1 to 1, DenseNet 169, 201, like that, right? So 1 to 1 is only taking 7 million parameters, but if you choose 169, it will take more than 9 million parameters, like that. What is meant by hybrid model? Hybrid model, in what sense you are saying? I mean, hybrid can be defined in many ways, right? So I mean, if you are talking about hybrid CNN models, then it could be like, if there are few works you will find where people have combined the two models. Like, let's say if you want to combine, VGGNet and ResNet together, or probably ResNet and let's say DenseNet together, and then you will train the whole model or fine tune the whole model, then it can become a hybrid model. And also there are few works which we have seen where people have extracted the features from the traditional approaches, and they have fused the features with the CNN features, and then pass the images into, pass the features to some of the classifiers. That also we have seen. So there are a couple of hybrid models you can see, but these hybrid models you need to check that whether there is a need of hybrid model or not, and why do we need hybrid models? Because it sometimes leads to high computational complexities. So that also we need to be very careful, that is there a need of hybrid models. So if there is a need, then of course, I mean, people have also combined, let's say hybrid is if you're talking about hybrid, so you might have heard about something called as a transformer model, right? So now it is very popular region transformer model. So people have combined, convolution and transformer model known as convolutional transformer, which we also did some of the works, interesting works. So how to combine, convolution, null neural network and VIT network together to have a hybrid model, right? So those kind of hybrid models can be done because both are having different characteristics, right? Okay. So I hope I have answered all the questions, right? So, and let us now move on to the next session. I'll take just 1 minute of break, right? And then I will start the next session. I mean, okay.